first talk, great talk by Adrian. Thanks for that. The one takeaway still ringing in my head is if you're going to say, I need to set up Kubernetes to run my app, that's the wrong level. But I'm going to say, I need to run my app on Kubernetes because he already did a great job convincing you guys that's the right thing. So you got to be cloud native, ready to go, recomposable, so on and so forth. So this talk is about demystifying Kubernetes StatefulSets. If you're trying to run an app on Kubernetes, it's easy to deal with the stateless layer, relatively. The stateful layer, data, has a lot of gravity, and we're going to talk about what Kubernetes offers. Okay? Quick background. I'm one of the founders and the CTO at Yugabyte. We started the company about a couple of years ago. My co-founders, Kannan and Mikhail, myself, and a whole bunch of others in our team, we worked at Facebook, putting a lot of large applications into production. Facebook Messages, Messages Search, our operational data store dealt with alerting and time series, fraud detection, so on and so forth. And we all did this on top of a common platform, and that's the secret sauce that goes into the database we're building. So we're going to talk about Kubernetes StatefulSets in the context of a real example. The example application we chose is naturally Yugabyte database. So before we go into the StatefulSets, here's a quick overview of what Yugabyte was built for. At the core, Yugabyte is a transactional database. It has a document storage at its core. It provides distributed ACID transactions, and it provides strongly consistent replication using Raft. Okay? It also is a highly performant database. So you can tune your read latency to get really, really low read latency, sub-millisecond read latencies. And it also does very well when you write or read a large amount of data. So streaming ingest, batch reads, so on and so forth. The third attribute of being cloud native, and Adrian touched on it many, many times, is to distribute data across the globe. So globally distributed data store. And Yugabyte is really good at doing that as well. So global data distribution with automatic sharding and load balancing. Now, obviously, a database built today should be cloud native, and that's what we aim for. So it's built to run on bare metal, on VMs and containers pretty natively. It runs pretty well there. It's a self-healing and fault-tolerant database. So most common types of outages when you run in a geo-distributed fashion, they're taken care of. And finally, it's open source. Actually, we like to call it double open source because it's open source Apache 2.0, but it also builds on top of open source APIs such as the Cassandra query language, Redis API, and Postgres. Okay, so let's look at how Yugabyte, so Yugabyte does all that, right? So now let's look at how it's deployed without containers. And then we'll use that to derive the motivation for StatefulSets and go on to look at an application built on top of StatefulSet containers using Yugabyte. Okay, so that's going to be the rough outline of the rest of the presentation. So Yugabyte has two top-level processes that are important. These are highly replicated and available services. The first one is the YB master. The master is a metadata manager for the entire cluster. It takes care of placing the right number of copies across fault domains, re-replicating data, coordinating a lot of cross-cluster background activities, such as table creation across all shards, distributed backups, so on and so forth. The second process is the process that does the I/O, right? And this is very similar to Kubernetes' own infrastructure, architecture. There is a highly available master, there's a master, and then there are slaves. These are called tablet servers here. They own pre-sharded chunks of data called tablets. And the tablet server has a document-based storage engine at the core, which is a heavily optimized and extended version of RocksDB for ever-growing data. It uses Raft-based replication to maintain consistency of data across different nodes. And on top of that, it has a distributed global transaction manager for you to perform single row as well as multi-row transactions, right? So you can build secondary indexes and other useful constructs on top of this diagram. Okay, so this is how Yugabyte cluster is started if you're running inside VMs or in a bare metal setup. You start the masters by passing various addresses and the data directory. Of course, there's a ton of options to customize it, but this is the simple view. Now, if we're containerizing this, putting it inside Kubernetes, what would we need, right? The first thing that we need is a notion of order, right? You need to do rolling restarts, scale up, scale down, which is add machines, add containers or pods, remove it. So the first thing is ordered operations. The second thing is when you write your Kubernetes YAML, you need to be able to reference machines that have not yet come up. So you don't know their IP addresses. So the second thing you need is a stable network ID. You need to know how to reference the machine before it's come up. The third thing you need is a persistent volume. What this means is if my process restarts or my pod dies for a software upgrade, I shouldn't lose all my data, right? So the new incarnation of the pod should attach to the same disk, right? So those are the three core constructs that you would need in a stateful service, right? So now let's look at map all of this to traditional Kubernetes controller APIs. So you've got a replica set, but that's not for storage, so it's only for ephemeral storage. You have a deployment, which deals with a set of replica sets, like a group of replica sets, and offers you how to do upgrades and so on and so forth, scale up and scale down and all of that stuff. So that's clearly not for stable storage. You have a daemon set. A daemon set, you cannot foretell, like you cannot predict its IP address, so it doesn't have a stable network identity. So that's not a good choice. And finally, there's a job. Well, that's great if you want your database to run for 5 minutes, but it's not really a good database at that point. So that doesn't really cut it. So if these are not the constructs, what is, right? And that's where the StatefulSets API was introduced into Kubernetes. If you look at the development of StatefulSets, quite a bit of thought has gone into building this. It's taken 1.5 years to get into a stable state from the time it was started, and it has a lot of useful and powerful constructs. So let's dive right in. The first thing is a stateful set gives you ordinal indexes for your pods, which means if you launch a replica set, 5 replicas, it'll give you numbers 0, 1, 2, 3, 4, 5. If you scale it up, you get a new one, number 6. If you scale it back down by 2, you lose 6 and 5, and you have 0, 1, 2, 3, and so on and so forth. Right? The second thing is a stable, unique network identity or name, so you can reference these pods by their ordinal numbers. So we'll see an example pretty soon, but you'll be able to say pod number 1, pod number 2, and so on. The third thing is persistent storage. So depending on the type of storage, your storage will follow the new incarnation of the pod, right? There are nuances there. We're going to look at that. But roughly, if you restart your pod, if your pod dies and restarts, you wouldn't lose all your data and you have to re-replicate. Finally, there is a mandatory headless service. This is something we did not talk about in the previous slide, but you need to be able to discover the set of pods or machines running inside the service, right? So if it is so flexible that you can add and remove pods all the time and survive machine failures, then it becomes difficult to enumerate what's currently running as a part of the service because it keeps changing. So you need a way to discover all of the members of that set, right? And that's the headless service construct. Okay, so now that we looked at the basics of what a stateful set is and what are the features it gives, let's map this back to the deployment we talked about, right? When we talked about the VM or the bare metal way, how would you deploy Yugabyte as a stateful set? Now you have your nodes, 4-node example here. There are 2 services in this example. The first stateful set service is the Yugabyte master, right? When you're doing a replication factor of 3, there are 3 pods that are spawned. They're called YB master 0, 1, and 2. Okay? And you will be able to reference them using a CNAME, right? And we'll look at what these CNAMEs are a little later. Similarly, the YBT server has 4 entries, and these are the guys that serve data. You'll be able to scale up and down pretty easily. The masters are exposed to the external world using a headless service. So if a new tablet server comes in, a new pod comes in, and it needs to discover what are the masters, because we need to pass it the address, you just pass it the CNAME. It enumerates all the pods and goes and figures out who it should talk to. So that way, these set of members can be completely dynamic. You can change machines, you can change everything, but the new guys coming up will be able to discover them. And in Yugabyte, you have all of the clients, which is the apps that are working, actually talk to the tablet servers, so you'll be able to discover them through the YBT server headless service. By the way, guys, if you guys have questions, please shoot, because I think it makes it a lot more interesting, but otherwise, you can hold it for the end too. Please, yeah?
If you run a replica set with like more than one replica, are you guaranteed that they'll match the nodes?
The question was about running replica sets and the guarantee of which nodes they get placed on, if I'm right. Replica set, I assume you mean is the replication of data between these parts, or are you talking about the controller API replica set?
Well, like if you specify like replica set with like 3 replicas,
Uh-huh.
I mean, I guess what if you have 2 nodes in the cluster? What's going to
Yeah, great question. So his question is, how do you decide which replica goes where? We're actually going to look at this. This is called anti-affinity. Great question. It's coming up on one of the following slides, but it's actually an excellent question. So, okay, so the app clients talk through the YBT server headless service, and the admin clients, like for creating masters, or internally the T servers talking to the master, happens through the YB master headless service. So go recode. So let's go right in. The first thing, and this is the YAML for, and all of this is open source, so you guys can find it on the Yugabyte repo, GitHub. We'll share all of that pretty soon. But the first thing you notice is you set the cluster IP to none, which is the way you declare a headless service. You say that I don't want a specific IP, maintain a CNAME for me, like a DNS name, that I can resolve to find the members at any point of time, and keep that domain name up to date, the DNS name. The second bit is you want to say what your replication factor is. So if you have a replication factor 3 cluster, you need 3 replicas of the master. So your data is replicated 3 ways. So that's what that says. Oops. Okay. This is actually the CNAME that you use to discover the masters. So it's called ybmasters dot, and then you have a namespace and your deployment and so on and so forth. So that's how if you go and resolve that, you'll be able to list all the masters. And finally, you expose certain ports, and you have a certain data directory mounted. So that's how the master service looks. The tablet server service, not very different. Another headless, like a CNAME thing to expose for discovery. You have your replica sets here. This is actually the number of nodes in your cluster. How big do you want your cluster to be? Do you want 3 nodes, 4 nodes, 5 nodes, so on and so forth? And you can change that on the fly. You are giving the master CNAME for it to discover the masters. And finally, you expose the ports. The only thing here is you expose the ports. The 9042 is the Cassandra query language port, and 6379 is the Redis port, because Yugabyte offers you to talk to it using a Cassandra query language or Redis in a single database. So it's Cassandra and Redis as a elastic database, right? Okay, so Yugabyte is not the only example. There are many examples of stateful sets, Postgres, Zookeeper, Kafka. So you can go look it up. The principles are somewhat similar, right? When you're composing these services. But we're going to look at some of the finer details, like the question about where to place replicas. Okay, so first question that comes up pretty often, should I use local attached storage or remote redundant storage, right? Like a remote persistent volume. So local attached storage just got released in Kubernetes. It's in the 1.10 release. It's in beta, and it lets you model a persistent claim on top of a local disk pretty easily. But some of the advantages of going local for a distributed database like Yugabyte, which has built-in resilience, is that you will get lower latency and higher throughput, and of course lower cost, because it comes with the machine. You don't have to provision a new disk. But if you go remote storage, you get higher latency and lower throughput, because the remote storage, like a SAN, does its own work to do replication and fault tolerance, which is not needed for a database like Yugabyte. But if you, and of course, Yugabyte does its own replication and fault tolerance, right? So, but if you go for an RDBMS, a traditional RDBMS like Postgres, for instance, you'd have to build the replication at a higher layer. So in that case, it's preferable to use a remote store so that you don't lose your data when the pod goes down. Finally, like The local store is typically provisioned outside of Kubernetes because it's attached to the machine. You need to get a machine that supports local SSDs. But the remote store is dynamically provisioned because it's a remote volume, right? So that's like a persistent disk in Google or a EBS SSD volume in AWS and so on and so forth. And finally, latency sensitive apps, better to go local, at which point you probably need a distributed database. All right, so I think here's the question that you had asked about, how do we place data? So there is a notion of anti-affinity. So what that says is that you can place pods of a single service on different machines, right? So what we're saying is you don't want all your pods on a single machine if you just have one machine, because if it fails, you're done. Not very useful to replicate data at that point. So we ask it to enforce anti-affinity, and in this snippet, we say, if the app is a T server, then make sure its pods don't sit on the same machine. So that forces it to move across different machines. Of course, you can control whether you want to kind of forgive this rule when you're actually scheduling and you don't find a machine, or you want to say, hey, that's an error, I'm not going to schedule the pod. So there's different strategies that you can do in order to accommodate that. Yugabyte can run multi-zone, multi-region, multi-cloud. So it's a database that, and you can run on-prem, on-cloud, hybrid, all of these deployments, right? But we're working with the community to figure out how to achieve this in a Kubernetes native fashion. Now, some of this stuff is about the Google Kubernetes Engine, GKE. Yeah, I don't know if I should be saying that here, but anyway. So multi-zone allows you to tolerate your slaves being across zones, but your master in a single zone. A regional deployment has your masters and slaves across multiple zones in a single region. And a multi-region deployment requires federation, which Kubernetes is working on, like people in the open source working on it. And we're collaborating with them to make sure this works for stateful sets. Okay, so what's the use of all of that stuff if you can't build an app on it, right? So it's all about building an app. So you've heard of the MERN stack probably, but with Yugabyte, we have converged different types of APIs into a single data platform. We offer a JSON data type that we're working on so you can model flexible documents, and we offer Redis as a database so you can have truly unstructured documents that you can put inside. So you can use Yugabyte as the database, Express and Node.js as the REST API layer, and React as the UI layer. And I'm going to show you an example of an app that we built using this stack. It's a pretty popular stack, right? So, and all of this is deployed on top of Kubernetes. Okay, so the app itself is open sourced. Like you can see that on like the Yugabyte/Yugastore on GitHub. So you guys can check it out. It has instructions to deploy it. You can try it out on your laptop, so on and so forth. But we looked at the deployment for how a Yugabyte DB deployment looks, right? Like what we had was a headless service for the master with a bunch of pods, and then a headless service for the tablet servers, T servers. They talk to the master through this headless service to discover the masters, and these guys are now the database themselves, right? Notice that if you want an external world agent to be able to view the UI or the dashboard, you need a load balancer on top. Right? The load balancer round robins the request across the set of pods that it's managing. So it works that way. And the app that we have, this React Node.js and Express app, is running inside a deployment, which is one of those scalable constructs, replica set constructs that Kubernetes offers, with a load balancer on top. And it is using the T-server headless service to discover the various tablets. Okay, so at this point, maybe I'll jump quickly into showing you all this. Okay. Yeah. All right, cool. This is good. Hands free. Okay, so if you remember the diagram, right? Let's look at the different pods in the system. So what you see here are 3 masters and 3 tablet servers, right? Oops. Okay? And what you notice here, I just pulled up the physical IPs that they have. And what you will find is that, I mean, the way Kubernetes, or at least in GKE, the way it's distributed is you'll find that the third number here represents the actual node that the data is deployed on. And because the anti-affinity rule was specified, you'll see that each of the masters is on a different node, and each of the tablet servers is on a different node. Okay? So, and we talked about a Yugastore deployment here. So the pod that Yugastore is running on is right here. So this, and it has a bunch of expletives-like looking stuff, like, you know, like at the end, which you could never guess if you launched a new pod. So, I mean, but that's just one of the pods inside a deployment. So that is the Yugastore deployment itself. And these are the various services that are running in this deployment. So what you have here, a load balancer for the UI, a load balancer for the Yugastore app itself, and you have the masters and T servers, which have a cluster IP of none. So it's just a CNAME. It's not for accessing it from outside, right? So this is what we did. So let's go look at this app, right? So I have it deployed and running. So that's the app. But before we get there, so if you look at the IP address here, this is the external load balancer that lets you get into the YB master admin UI. And so that's the same IP address here that we've exposed to the world. And what this says is it's a three-way replicated cluster across these three pods. And they could be living, in this example, they live on the same cloud, region, and rack or zone. But you could have deployed them cross-zone, cross-region, cross-cloud pretty easily, right? The data just has to flow inside. And it has a default replication factor of 3. And you can go to the tablet servers and see that right now there's no load. And these are the 3 tablet servers, right? And you can scale this up and down on the fly. Now, let's take a look at the app itself. The app is a bookstore app. It's like pretty standard, nothing fancy here. So it's got a whole bunch of books as the product in it. And you've got the products categorized into some top-level categories. So you have business books, cookbooks, mystery and suspense books, sci-fi books, and so on and so forth. So these are more static categories. And then you have some dynamic categories like show me the highest rated books. And so it's going to show you across all the users that rated these books what the rating is, right? Or you can say show me the most reviewed books, right? And it's going to give you the books with the maximum number of reviews. And I wish that were all real, but these are all fake data generated. But nevertheless, it still makes its point, right? So how did we do this on the database side? So I'm going to connect to the database and actually show you how the data was laid out. All of the static stuff is put into Cassandra as a database, and all of the dynamic stuff is put into Redis as a database. So you don't really need to deploy multiple different data stores in order to build your app. So I'm just going to connect to one of the T servers because I know its name and I don't need to go through a discovery process. And what I have is a shell into the database itself. I've connected through one of the tablet servers. Now, I'm going to say, I mean, it looks pretty much like SQL. So what I'm going to say is give me a whole bunch of attributes from the table yugastore.products where the category is business, and give me just 3 books in that list, right? And so running that is going to give me 3 books in that list, right? And similarly, I'm going to say, OK, fine, that was great, but give me all the business books that are hardcover books, because we have another attribute here that says hardcover. And doing that gives you all the hardcover books. So this works great for static categorization, but when you're trying to do show me the top 5 reviews, right? That's a little harder to model on top of a traditional SQL-like system. Like you'd have to do a lot of inserts and deletes and so on and so forth. So for that, we have the Redis API. Right? So now you can connect to Redis. It's the same data fabric underneath, but exposes a different table through a different API. And you would say, give me the top 5 books by the total number of stars that they received, aggregate stars, And it shows you that book ID number 2 got 4.81, and 3 got something, and so on and so forth, right? And it's pretty easy to update the set in Redis. Similarly, show me the top 5 books by reviews in the descending order, and you see that data show up, right? So it's pretty easy and flexible to build a multi-model application, and since it's the same database, you can scale it, you can move it, change cloud, change zone, go on-prem, on-cloud, whatever it is, do async replication to a faraway zone to serve data with very low read latency while maintaining your write consistency in a global app, and all of that becomes really, really easy. Okay, so the other interesting thing that I thought would be useful let me attach to one of these. Okay, so I just attached into one of the pods that the tablet server is running on. And what I can show is that the data is on these mounts, disk 0 and disk 1. Right? And the way the pods are scheduled, they get scheduled into a node pool, which has a locally attached SSDs. So these are just the raw disks that get mounted through, and the pod uses them, right? And because they have anti-affinity, you don't expect to see multiple of these guys fighting over the resources of any one node. Okay, so yeah, before we go, yeah, I think I forgot to show that you can click into a book and actually see its details, but I thought that was pretty obvious, so but you see that this has an item number, item 5. So let's turn on some load into this system, right? Oh, I'm in the pod, sorry. Okay, so I just launched a program that just clicks on pages at random. So, so this is just like the bot traffic that you pay for. But what you see instantly is that you have data that's, like reads and writes that gets, where are they? Here they are. So reads and writes that get distributed across the different pods, right? So, and as the app scales up and down, you'll be able to scale your data, like the data side of the whole thing, pretty easily. So if you want to do that, let me go to a different window. So this is the replica for the master. This is the replica for the tablet server. I'm going to change this replication factor to 4, right? And you just apply it, and what you will see is that it configured this guy. You'll find that we just launched a new pod. If you remember, there were only 3 before, 0, 1, and 2. Now there are 4, 0, 1, 2, and 3. We can go here and verify that there's a 4th guy that just came up. So you see that a 4th node started coming up. The number of tablets were evenly balanced across 3 nodes. Now they're starting to move to the 4th node that just came in pretty seamlessly. And instantly, a small portion of the traffic starts getting redirected to the 4th node, and with all your replication, fault tolerance, all of that stuff. And over time, you'll see that, the system is built to move from one set of nodes to another, add nodes, remove nodes, all of that in an online fashion. So tomorrow, you want to go from one availability zone to another. You want to go from single AZ to multi-AZ, on-prem to on-cloud, one cloud to the other. All of these transitions, or even a much more simple problem, just change machine type. I don't know how many of you guys have gotten bitten by that, but oh man, we had that quite a bit at Facebook. Oh, you get like 6 months, just move your data out of these machines to the new machine, and yeah, like it finishes in 6 months. But whatever. So, so what you see is that all of these transitions are built to be online. So over time, you'll see that all of the tablets get equalized. So the number of tablets or internal shards will get equalized, and you'll see that the read and writes get spread across the nodes in an even fashion. Okay. Okay, so that was the demo. So So either it was incredibly easy to understand, or I've just been very cryptic, but yeah, please, thank you. Yeah.
So you spoke about shard, but you never spoke about how is the sharding index being mapped, who does that?
Yeah, great question.
Great
question. So question is, I spoke about shards, but not about who does the sharding. The master does the sharding when you create a table. So the minute you create a table, there's a configurable number of shards, which is defaulted to a sensible default, or you can specify and override as you like. And the master does the splitting and placement of shards and their replicas across all the tablet servers. So if you have, let's say, let's take a relatively complicated setup. Let's say you have one copy of the data in US West, one copy in US East, and a third copy in Ohio, US Central, right? So if you have these three fault domains, the master will split these shards and keep one copy of each of these shards across the three domains and set up a raft replication pipeline between these guys. So the shards are highly consistent and highly available. And if a node fails, like if you lose entire US Central, right? Or like US East or whatever, right? Then the re-election of the leaders happens in a matter of seconds. So you will have a very highly available system, but at its core, it's a consistent and partition tolerant database. Please, yeah. We are strongly consistent. In fact, we are transactional. So we offer single row and multi-row ACID consistency. So you can do distributed transactions across keys or on a single row. So but by default, we are strongly consistent.
How do you compare this Cosmos?
Great question. So how does Yugabyte compare with Cosmos? I'll answer that with a hybrid. And I should really not be saying this, but I will take Cosmos and Spanner as the two databases. Cosmos is a multi-model database, but does not offer global consistency with transactions. Spanner is a globally consistent database, but offers only SQL as its language. With Yugabyte, we have a multi-model database that offers global consistency. So you can pick and choose the API you want. We're working on Postgres. We already have Cassandra, and a good portion of Redis supported. You can model your workload. So you can use Yugabyte for a streaming ingest-like workload for your time series data IoT, and also have a couple of tables on which you want to do absolutely consistent distributed transactions at the same time.
One other question, to be strongly consistent, do you expect any SLAs from the...
Yeah, great question. Yeah, so do we expect any SLAs to be strongly consistent? I will answer that with a nuanced answer, because we try to be highly performant with globally distributed transactions, and that is kind of like bending the laws of physics, which is why for single row ACID, we don't need any SLAs, we just network latency is what you need. If you're doing distributed transactions, we can integrate with an external atomic clock service like Amazon Time Sync service, or if you don't have that, we can just work with NTP, but your latencies are going to be high. And that's just laws of physics, right? But your consistency is guaranteed. So a lot of applications want strong, a certain type of workloads and applications need absolutely strong consistency across regions for writes, but low read latencies. Some of them are okay with giving up that write consistency a little bit, as long as it eventually reaches there using an async replication pipeline. We can cater to both sides in 1 DB. Please, yeah.
Performance-wise, how does Yugabyte compare with other?
A wonderful question. How does Yugabyte compare in performance with other databases? We benchmarked Yugabyte against Apache Cassandra. We have a blog about it. In fact, I think I'll pull it up as we speak. Yugabyte offers sub-millisecond latencies even when serving data from disk. We benchmarked this on a Google Cloud with the cache size as just like, I think, 7.5 gig, and the data set size being much, much larger on a 4-node setup with 8 cores, I believe. But anyway, we were able to do 70,000, 80,000 operations per second on that cluster with 880 microsecond latency. And it's all forced from disk, right? Because it doesn't fit in memory. But if you're going into the in-memory side of things, it drops even further, like in the 200 microsecond latencies. So that's typically our range. Like I said. Yeah, it was a terabyte or 1 point something terabytes. Most of this information is in our blog. I will pull it up. I will answer your question live. So it's a 1.4 terabyte data set, 4 nodes, 8 cores, 7.5 gig RAM, 880 microseconds, 77K uncached reads. So that was that workload, and we have another post here which talks about how I hope I can find it, yeah, here. So how we're building a strongly consistent Cassandra API with better performance. So that's the P99 on a YCSB benchmark, like it's a popular benchmark with a Yahoo Cloud Serving benchmark that does a variety of different operations. The green is the number of operations per second Yugabyte does, and blue is what Cassandra does on the same type of hardware with like, similar type of workload on top. So.
I'm storing time-sensitive data, which over time the importance cuts down. Is it possible to have a policy where the more recent data is kept in like a Redis-like fashion, which is more easy to access, and over time we send that data to a more store, which is
yeah, beautiful. So question was, if there is an app that generates time series data where recent data is of bigger value and older data is less valuable, is it possible to tier the older data to a cheaper store? Answer is yes. Thank you for asking. I was dying to tell you guys that, but anyway. But the question I think on top of that is, can we do this using a Redis API? You absolutely can, because Redis or Cassandra is just an API to us. The core database is the same. So you will be able to, and most of the core things needed for this feature are already in the database, but we're enabling this at a higher level in the DB. So what you can do is have an SSD disk mounted for your recent data, and you can have a bunch of EBS hard disks or S3 mounted as your cheaper tier, and we'll be able to natively move data between these as it gets older, colder, etc. And if you really don't care about the very, very old data, you can set a time to live on the table, and we'll just expire out the oldest data. Yeah, please.
Did you use Jepsen as correctness?
Yes, we're working on Jepsen. That's in progress. We've done a bunch of testing in an ad hoc manner in-house, and I mean, it's not that ad hoc, it's very sensible to us, but maybe not to the external world in a formal way. We've done things like rolling upgrades, kill a node, start a node, add a node, remove a node around the clock every hour or every 2 hours. With a lot of data density, because it doesn't matter if you do it with a few gigabytes, it matters if you do it with hundreds of gigabytes. So we've already done that. Jepsen framework is something we're working on. You can follow us on our GitHub. We have a project for it that's in progress, and we fully expect to get certified by Jepsen because, we just love correctness in databases. So.
If there was one thing that you can mention that your database can do, the rest of the transactional database cannot, what would that be? And you can tell more. But just
yeah, so if you need a database that has transactional consistency, like low latency, high performance, and geo-distribution. So whether it's multiple nodes in one zone, multi-zone, or multi-cloud, all the way to planet scale, like across different geographies, the whole range, that would be Yugabyte. So that's what we're very proud of. We have actually gone down to the level of extending Raft with async replica observers to give read replicas so that you're able to reason about consistency without sacrificing geo-distribution and performance.
Sure. Actually, do you support connections across documents and does it?
Yes, we do support that. If you go to our docs, you guys can try this all out on your laptop, by the way, whatever I'm saying. If you go to our docs and if you go to the quick start section, it'll just guide you through how to install it. But if you go to our explore section, docs.yugabyte.com, you can click on the ACID transactions, and you'll see a very familiar banking example. In this example, this is a Cassandra query language, so it's like a table which looks pretty similar to an SQL table. You have an account name, an account type, and a balance, right? So it's people who have a savings account, checking account, that's the type. The name is the name of the person in this example, and the balance is the balance, right? And you'll be able to do, you just insert some toy data, but you'll be able to do transactional updates such as begin transaction and then transfer some money from the savings to the checking account. And the second example that it talks about is if John wants to transfer $200 from his checking account to Smith's checking account. And these are across nodes, across shards, so we already support multi-document transactions. Yes, please.
So is it already stable?
We are in the 0.99 version, 0.9.9. We are pretty much stable because we have customers, so we have a promise to keep it backward compatible with them. But our 1.0 is, we're going to announce our 1.0 May 1st. with KubeCon. So we're traveling to Copenhagen and we're going to announce it as a part of that. So it's just a matter of time. So pretty stable. Yeah.
So where do you see the Yugabyte cannot be a good fit, like in what cases? Because you cannot have all the green boxes checked. Right?
Absolutely. So question is, when is Yugabyte not a good fit? I will answer that with the different APIs we support because that gives you an idea. For Redis, if you care about 20 microseconds versus 200 microseconds, we're not a good fit because Redis takes process isolation to the single-threaded process level. It only runs sticky on a core. It has its roots from a memcache derivative, so it's really, really low latency. We believe that most applications that we're targeting should not need that low a latency. So if 20 microseconds, not Yugabyte, but if 200 micros is good, then that's great. Yugabyte is a good answer, right? But we give you persistence, scalability, all of that stuff under the hood, whereas with Redis, you'll have to deal with sharding, like persistence, that whole enchilada, right? So that's one thing. On the Cassandra side, if you write data and you're like, I don't really care about it coming back, that's not our cup of tea. So there are some deployments where you don't really care about the consistency of your data, right? So sometimes you just are okay with eventual consistency. So we don't want to deal with eventual consistency. That's not something we offer. If you ask us philosophically on the side, we'll tell you it's a bad idea to build that anyway because async is better than eventual consistency. But anyway, that's not a use case we handle.
And another question, how does it compare with the cockroach DB?
Yeah, question is how does it compare with cockroach? I think that was the third API I didn't mention, I should have, but we're working on SQL as well. We don't support joins. It's in our roadmap, but philosophically we believe that you scale out to decrease latency. If you have joins, you don't have a control on how data gets placed across different nodes, and a join will have to visit more nodes. As you add nodes, the number of nodes increases, so your latency typically increases because some nodes won't perform as well as others. That's just like the way it is in a large deployment. So we don't support joins today. It's in our roadmap, but we are focused on OLTP applications that serve foreground workloads as opposed to a full SQL compatibility, although that's in our roadmap. Now, the second piece is even with a Cockroach DB, because it's not a low latency type system, you would still need to supplement it with a cache on top. So typically like a Redis or a Couchbase or so on and so forth. With Yugabyte, you don't need a separate serving tier. Yugabyte is low latency enough to serve as your serving tier.
How many max nodes clusters?
We have tested up to, so that's another thing that we have in our blogs. We have tested up to 50 nodes. And it's not that, and we're very comfortable as a team running hundreds and hundreds of nodes. We did that at Facebook. It's just that, at some point you're starting to pay Amazon, and all the money doing the testing. So that's why we stopped. But yeah, it's there in our blog somewhere. So.
Last question.
Yeah.
When you're supporting multi-models, right? You have Redis, you have Cassandra, whatever the SQL model. So you have with backend different engines which serve.
So question is, for multi-model, do we have different engines? No, it's the same core. So it's a document-based core. We just allow you to access that through different APIs because in 2018, there are so many databases with so many APIs, we felt it's a burden to get people to learn one more API. So our mantra is like, hey, it's like Cassandra. You know how to write a Cassandra select statement, except now you can write begin transaction. You can do like a variety of other things. It's like Redis, but we added a couple of more data types because that makes it a lot more powerful and so on and so forth. So it's the same core underneath.
The reason is I'm not a database guy, but when you write to a Redis query versus a SQL query, right? So the indexing, the query execution will be different, right?
Yes. Question is, if you write a Redis query versus a Cassandra query, the indexing and the query execution layer is different. It is. We have a pluggable query layer. It's called YQL, the Yugabyte query layer. It's a multi-model query layer. You can keep plugging in more and more query layers, but at the core, it's a DocDB at the core, that's the name we give it. It's a document-based core. We translate every query into our DocDB, and we enhance our DocDB to be a common stable core across all of these access patterns. And that's why, if you want to replicate data, all of that stuff, we're able to do that pretty easily. Yes, so Cosmos, yeah, exactly. So Cosmos is an example of such a database where you have multiple access APIs, but a common database core at the bottom.
So the storage is same, the transaction is different, right?
Yes, the storage is same, the transaction layer is different and pluggable, but it's equally distributed across nodes.
But just a last question, you don't see any inefficiency in going with those kind of models? I'm just trying to take.
Yeah, so the question is there any inefficiency in going with those models? And this is actually a lot of the learning we had from Facebook. And in fact, we have a blog post talking about that. Facebook has a distributed a MySQL setup. So it has a sharded MySQL. But one of the things they did in order to boost its efficiency on Flash, especially to deal with denser data, is they removed the InnoDB core engine and replaced it with a MyRox, a RocksDB-based storage engine. So, and if you look at like HBase and the things that we have done with like we worked on, we were the early guys on Cassandra before it was open sourced. We were the guys that worked on HBase at Facebook. All of these are also at the core a log structured, a log structured storage engine. So we have the common log structured storage engine along with all the lessons we learned from running this at a massive scale at Facebook, but we're able to adapt the data model according to the query language. So if done right, it should not be, like most databases are moving towards an LSM model anyway.
So Cassandra was like one of the blogs on Facebook that say that they are no longer operating Cassandra cluster, right?
Yeah, that was us actually, yeah. So question is, no, it wasn't operational actually. The reason Cassandra was built was for, sorry, yeah. So question, at least the statement was Facebook at some point said we're no longer operating Cassandra, and I was telling him that was us saying that, but anyway. It's because we were involved in building Cassandra and then we were involved in building HBase afterwards, but it's really the tool for the job, that's the reality. So if you look at your use case, you pick your data layers underneath based on that. We built Cassandra for inbox search. So this is like if people wanted to go search their messages, they would go to this system and search. Nobody wanted to spend money on this because inbox search is rarely read. It had to be very high write throughput, and it had to be highly available with very little maintenance. So cross data center was a must. If the data became inconsistent and somebody complained, we could always get their messages, reindex it and put it in, and it's done. But when we moved all of the messages, including chat and everything to HBase, we needed a consistent data store. So we moved from Cassandra to HBase, which offered strong consistency.
No, my question is not that. My question is like, do you suggest Cassandra for new workloads, like as it is like 2008? I know because the reason is like sometimes you have to model your Cassandra data model based on the query access and all things like that, right? So going forward, your queries might change, right? So the data model that all you're done will go for.
Yeah. So yeah, I got your question. So question is a Cassandra-like data model where you have to model your data based on queries suggested because your query pattern might change. The reality is in a scale-out system where you need low latency of serving, you need to do that anyway, right? So we will offer the way to munge and change data. We already offer Spark integration to do that if you need to transform your data under the hood into a different serving pattern. But the kingpin of serving in a scale-out structure is to really make sure you denormalize your data and have it stored with multiple replicas is fine, but it has to be in the serving pattern because you need low latency.
Yeah, last question. This, how does the auto sharding happen? Like, it depends on the way you define your data model. Like,
yes, the auto sharding depends on the data model. Like in one of those examples, you can say which key or subset of primary keys you want to shard data by and which ones you want to sort it by. So we can do that offline if you want. Yeah, I think we want to give a couple other, but great questions. We should talk offline. So, okay, so I will take your questions, guys. I just will have one more slide. I'll just finish it because I thought it was going too fast, and now they're great questions. So, okay, so we're thinking of extending Yugabyte with Kubernetes operators. An operator is a way to codify human knowledge into the system so that what a human does and keeps repeatedly doing in an error-prone fashion, the system can do better. So the typical pattern, and here's an example. I think Adrian talked about how you don't need to shut down servers that are not used and add servers that have to be used and so on. So an auto-scaling ability for a database is an example of that. The Kubernetes operator works in this pattern at a high level. You first observe what's going on, you analyze the data, and then you act on it. So in this simple example, you observe the CPU usage of your T servers as a cluster. You analyze it. If the CPU usage is more than 80% or whatever number you want for 1 minute or something, and you haven't increased over your max threshold, always set a max threshold, otherwise you'll be paying a lot of money. There can be errors in that too. So if it's not exceeded, then add a node, right? And then repeat this process in a loop so that you're able to scale out and you can do the inverse to scale down, right? So that's an example of an operator. You don't have to have a person come in and check this and make sure it's running and so on and so forth, yada, yada, right? So you just need an escape hatch if there's an error in the system, which is why you set thresholds as max and min and so on. So that's something that we are working on. Talk to us if you guys need more information about that. Anyways, stateful sets are getting more powerful, so just summarizing real quick. You need to, even though they're getting more powerful and they're giving you a common way to think about how to deploy on any cloud, it still requires a reasonable amount of thought about how to achieve high performance and resilience. And some of the things we talked about here are highly applicable to Yugabyte DB, and there are other databases that you have to think through. Operators are going to make life easier. We're going to build them so that your life gets easier. And there's a big community that will help you if you want to get started. I don't know why I'm walking back and forth. Yeah. Okay. Yugabyte DB is open source under Apache 2.0. We would love for you guys to join us, watch us, star us on GitHub, our GitHub repo, Yugabyte/YugabyteDB. Try it out, and our docs only take a few, our docs are great, pretty easy to use, just takes a few minutes to install. You can try it on your laptop. You can try a variety of different failure scenarios. You can understand how sharding works. You can replication. I think a lot of these things you can just try out, and they're pretty easy. There's a descriptive doc for each of those in the explore section. Yeah, that's all I had, so please feel free to ask questions. Sorry, I think there was somebody here, maybe they left, I don't know. Question?
By scaling down, you need to reduce the amount of data in each shard. So you have to compress that shard and remove it.
We don't scale down by decreasing the data in a shard. We scale down by assigning more shards to a single node. So you'll be able to, so the minute you remove a node, we'll be able to redirect its shards to other existing nodes so as not to violate your data placement policy. Question was, what happens when you scale down? Do you decrease the data on a single shard?
Can you talk about why you use headless service instead of the regular service in Kubernetes?
Sorry, use what?
The headless service.
Oh, the headless service. Why do we use a headless service instead of a regular service? A headless service maintains, so if you have a group, right, a group of pods, a headless service maintains the membership of that group. If you add a pod, it will add one entry to that CNAME. If you remove a pod, it will remove an entry to that CNAME, because that's what is the purpose of a headless group. I mean, a headless a cluster IP, right? A headless service. A regular service, on the other hand, is like a load balancer, where if you hit it, it's going to redirect it to any one IP. So we don't need to do that. We want to know who is in that group. So our smart clients can directly go to the server that hosts the data. Okay.
Last question.
One second. We'll come here.
So I do not have to run into the container, right?
No. The question is, do you have to run it in a container? No. Yugabyte works bare metal, VM, containers, anywhere.
And if I'm going to run in a container, what are your memory requirements?
Question is, what are our memory requirements if we run it in a container? I mean, we can run on pretty light machines, like 2 core and a few gigs of RAM, but the reality is, if you're going to run this for a reasonable production style workload, typically you want around 8 cores or so. I mean, it depends on the workload, really. So you can start with pretty low, but I think it's hard to answer that without the workload characteristics.
How do you compare it to Cassandra? Because Cassandra is a real memory node.
So Cassandra, the question is, how do we compare with Cassandra? We haven't done the apples to apples comparison. All I know is, having worked on JVM systems quite a bit, they take a lot of memory because it's hard to keep reference pointers and serialized data. For us, that's not. We keep data prefix compressed in our block cache. Data is serialized. We can jump to offsets inside. We page very small chunks of data. So we're very, very efficient about it. And these are lessons learned at billions of requests at Facebook scale. So same architecture goes in, but not done the comparison. So
you were giving example of banking. So mostly banking are having relational database. So how do you migrate that?
Yeah, question is, in the banking example, most people use a relational database. How do we migrate? The language, if you look at it, is pretty similar to an SQL system. So modeling the table should be pretty similar. Now, some of the things you can do on top are, as you add nodes, you want to keep some subset of data together. For example, in that banking use case, you want to keep all of an account's data together, right? So Cassandra gives you the ability to shard data and tell the system which subset of data lives on which node. So in this example, I'm going to go up to the table definition. So what we say here is we say, these double brackets, they say that I want to keep all my account data on a single node, even if you add nodes. And next to that, sort my data by account type. So it's very efficient to access an account. It's very efficient to access account name, very efficient to access account name, comma, account type. Also efficient to list all the accounts data for a given account name, right? So that's on one side. Now, if you're just talking about, and the queries are pretty similar and so on and so forth, like it's like select queries, it looks pretty similar, right? So if you're talking about how to migrate the data itself, you can export it to CSV and import from CSV. And we have a variety of other tools that help you move data into Yugabyte from other systems.
So it is supporting asset property transitions.
Correct.
Can you say relational database, or we cannot say relational database?
We cannot say relational. So question is, because we support asset transactions and other properties, can we call this a relational database? No, because we don't support joins. So if you're trying to do an inner join or an outer join or those type of constructs, we haven't added those. Again, it's in the roadmap, but we believe philosophically that if you're trying to build a low latency serving application, you shouldn't depend on that at the serving time. You should do that in the application where you know what you're reading from and which table you're reading from, or we offer some advanced constructs where you can place the data together so you can read it all together atomically rather than doing the join on the fly.
So it is supporting foreign key and constraint and those.
So question is, does it support foreign key constraint? No, we don't support foreign key constraint at this point. And those are the places where like your foreign key may live on another shard. So before you know it, you're trying to insert some data and you have to read from 4 different places, and that decreases your write latency. So that is something it's better to be explicit about. But again, in the journey to SQL, we'll discover like if there are some of these things, we would love to talk to you to figure out like why you would want it in the user-facing side of things. So.
Do you have any plans like relational database have triggers, stored call, functions?
So question is, do we have any plans for stored procedures or functions? Not right now, no immediate plans. And again, we want to evaluate on a case-by-case basis. So we have support for Spark for large-scale data migrations and so on. And it's better to integrate with something like a Lambda or a push-down function. Like that's closer to what people do app logic in. I mean, it feels like the number of people writing a stored procedure language is not that many, but again, it depends on discovery of what people want. So.
Legacy banking application has that.
Yes, legacy banking has these kind of stored procedures, but they are very, very hard to migrate between databases. So.
So you said that you are giving a strong consistency.
Yes.
Cassandra is based on the Gaussian protocol, but you said your strong consistency is based on the raft algorithm. So how the leaders, what is the right throughput? Because the leader has to be in sync with them.
Yeah.
It needs to commit before the follow. It cannot commit before the followers are in sync. So what is the right throughput? Like how is it?
Yeah, so question was, Cassandra uses eventual consistency and gossip, whereas Yugabyte uses strong consistency with Raft. What is the trade-off on the write latency? Typically in Cassandra, when you do a write, you send the write to 3 nodes, you wait for 2 to acknowledge, and then you're good to go, right? But the problem is, because there is no consensus protocol, when you do a read, if you read from the one node that didn't get the write, because only 2 got it, you wouldn't get that data. That means you have to read from a majority. With Yugabyte's Raft protocol, we do the same thing on the write path. So when you write, we use Raft, but we will send the write to 3 nodes, wait for 2 guys to acknowledge, and you're good to go. But on the read path, because we use a formal consensus algorithm, you will be able to serve it just from the leader. So you do 1/3 the reads, but same amount of writes. Now it's an all C++ system and optimized all the way down. So that's why we get our, and this blog post actually talks about a lot of details as to what we did in order to make Yugabyte highly performant. And these are all the lessons learned in production from places like Facebook and a variety of other deployments.
So if you have an application which is a read-heavy application, right, then this is not a recommended database?
The question is, if it's a read-heavy application, is this a recommended database? In fact, it is, because we perform 1 read while Cassandra would have to perform 3 reads on average. So this is going to be very, very performant on reads, and we've done a lot of work to keep the cache like very compressed and highly easy accessible, all C++ end to end, like and so on and so forth. So your read latencies are extremely low. So you get like microsecond, hundreds of microsecond level read latencies.
So related to the gossip and graph, so you have rewritten from the gossip protocol to Raft algorithm? So
question is, have we rewritten from gossip to Raft? Actually, no, we don't even use gossip. We just started with Raft. And some of the reasons why we picked Raft as the protocol underneath has to do with, like, we've seen the evolution from going from Cassandra to a system like HBase, which uses HDFS underneath, which uses not Raft, but a pipelined, consistent replication, to now we are doing Raft because you can actually change membership on the fly.
Any plans to support graph database?
We already support a graph database. We support Janus Graph on top because we are API compatible with Cassandra. So if you can go to our develop section, ecosystem integrations, and you'll see that we support Janus Graph. You can try it out. Gremlin syntax and all that. So this will walk you. I mean, you can install a local cluster and you can download and run the stuff, and the whole. It's gonna the graph of the gods example, all of that. Yeah. So.
If I'm running across geography, and in one geography, most of my writes come from that geography, but I want to do some reads to the other geography, which to serve some queries. If I get a partition, because it's strongly consistent, will you not serve many reads in the other geography?
Yeah. Question is, if you're getting writes from one geography and reads from another, and the geography from which you're doing reads gets partitioned, what happens, right? So, yeah, if it gets partitioned, it gets partitioned. So what you will get, and you have this ability to choose in your client at the per API level, you can choose to perform a follower read or a leader read. So, yeah.
What's your concurrency strategy?
What's our concurrency, like, can you explain?
In general, like if the two writes happening, right? Like
Got it. So yeah, so that's actually a very deep question because it depends on a lot of code paths, but at a high level, we deal with it. Like we deal with concurrency in a variety of ways. We try to detect if there is conflict. If there is no conflict, we let it go through in parallel. If there is conflict, we try to order it. So, and we have an MVCC, multi-version concurrency control on top, which makes sure that you see reads in the order in which the writes came, and it's not exposed until the reads are there. So it's a variety of things underneath, but we handle concurrency pretty well.
An application has control over like how to.
Yes, the replication at the Raft layer has control, like it goes into the Raft replica queue only after we have dealt with concurrency, and because we go through the leader and the leader decides the order of the writes, we can do that pretty efficiently.
And clients also has control over, right? Like how to, which concurrency strategy.
Yes. Oh, you're talking about isolation level. Yeah. So we support snapshot isolation at this point, and we are working on serializable. But yes, the client has control over that. Yeah.
Support the Mongo protocols, MongoDB.
Question: MongoDB protocols comes up very often. JavaScript or not, that's a debate in itself. But what we are doing is we have added, or we are like pretty close to finishing up the JSON data type. So you can store in the Cassandra query language itself. So you can store a document as a JSON object, and you'll be able to perform filtering, queries, where clauses, all of that stuff on the various attributes, including secondary indexes. So that's our path. We're not really doing a drop-in wire compatible protocol for Mongo. But we will give a path to modeling the same type of applications, and even with more flexibility, because you will have a formal table, you will have the ability to do hash partitioning, range partitioning, so it'll have a lot of those advanced constructs.
Full text search?
Question is about full text search. Yeah, not this year. Yeah, I think so. It's a common core, so we can keep extending, but not this year. Yeah. Yeah. Actually, yeah, Sid, thanks. So Alessandra is a project that's trying to do Elasticsearch on top of Cassandra. So we would try to integrate with a product like that and make them the application tier in some sense, and we'll be the database under. So that would be a closer strategy to what we'll follow. But yeah, or the other answer is, if there's a customer paying us a lot of money, maybe we'll think about it. All right. Yeah, there's a raffle for, I think it's an echo. Thank you, guys.